Hello everyone, good evening. This is Shweta from AstronEra and welcome to our Astro stream. We are doing this series with Ellen, who is one of my friends that I met long ago, and our course is about observational astronomy for scientific applications. And our today's topic is exoplanet hunting. So I hope you guys are excited. A little bit about Ellen. She's an optical research and development engineer from Millennium Space Systems, California, USA. And now, without further ado, I request Ellen to start with our today's session. Yes,
Awesome.
over to you, Ellen.
Is my screen sharing?
Yes.
Perfect. Yeah, so for those who are not at last week's talk, this is my second out of 5 in this series that I get to present here. Last week I shared about the satellite imaging and tracking project I've been working on. And again, my goal is just to share as much about my experience in the astronomy world as I can and start discussions about really useful and practical applications using simple telescope systems. Let me get this out of the way.
Ellen,
Okay.
just a moment. There is the Skype window that's blocking the PowerPoint.
I think it should be gone now. Is that?
Okay. Yeah,
Is that okay?
Mm-hmm.
Perfect. So a bit about myself. Like she said, I currently work in Los Angeles, California at Millennium Space Systems, which is a subsidiary of Boeing. We build small spacecraft, and I work as an optical engineer where I get to do a lot of optical testing and an assortment of research and development projects to help build up our optics capabilities at Millennium. I've been in the aerospace industry for about a year now, so I'm pretty new still, and I just graduated university from Cal Poly at San Luis Obispo in June 2019. So if anyone has questions about university or what it's like working in the aerospace industry, please feel free. You can find my Instagram. I wrote it there, Ellen Glad Photo. Please feel free to reach out about anything or after this session, questions about anything that I talk about. I love talking about this stuff. And you can also probably find me on LinkedIn as well. All right, so let's get into today's topic, exoplanets, and how we detect them. So the project that I worked on that I'll get into a bit later is probably my favorite research that I've ever done. I think it's awesome how much data we can get on these tiny planets that we can't even see with our own eyes. But first, some background. So what is an exoplanet? It's any planet outside of our solar system. The first confirmed detection was actually not until around 1990, which isn't that long ago. So I think we're really still in the early phases of collecting as much data as possible and really understanding how different solar systems are, or how different solar systems compare to our own. So total exoplanets detected as of about a couple weeks ago is 4,200, but there are thousands more exoplanet candidates, they call them, and these are planets that have data on them. There are telescopes that have observed them, but they're not confirmed because you need to take multiple observations and understand a few key parameters such as size and mass before you can officially confirm an exoplanet. And I recommend checking out the NASA Exoplanet Archive. Here you can find a database of both confirmed and candidate exoplanets, and there's also a lot of fun tools for working with the archive data as well. So there's a bunch of different detection methods, but the main two that have been the cause for most of these confirmed 4,200 are the transit method and the radial velocity method. So the first method is the transit method, and this is what I did my research on and what I'll be talking about primarily today. As a planet orbits a host star, from our perspective on Earth, there's going to be a portion of the orbit where it transits or passes in front of the star, like the image to the right. And if we continuously take images when this transit's happening, using a process called photometry, we can use those images to extract the brightness over time. And if we see a dip in brightness, like you can see on that light curve plot in the upper right, then that's really good evidence to a planet being there. The second main method is radial velocity. And this relies on the fact that a star does not stay still when there are planets around it. It actually has micro movements due to the small gravitational pull that the planet has on its host star. This also relies on something called the Doppler shift, which you may have heard of. And this is the phenomenon that a star will redshift when traveling away from Earth and blue shift when traveling towards Earth. So we see these differences in micro movements when we take spectroscopy of these stars, which is a method to view the light spectrum from a light source. And spectroscopy is something that I'll actually be talking a lot about in a couple weeks for another session. I'm not going to get into as much today, but that's just a brief overview of the radial velocity method and how spectroscopy can be used as well. So a bit more history with exoplanet detection. These are two key missions by NASA that have discovered a majority of our confirmed and candidate exoplanets. The Kepler Space Telescope was the first mission dedicated to search for planets in the habitable zone, which means it's in a certain range relative to the star that it can possibly have water on it. And its payload was a almost 1 meter diameter telescope with 21 arrays of 4 megapixel cameras, all combined into a large sensor called a focal plane array. And this telescope had a very large field of view, 12 by 12 degrees, which, to put in perspective, a lot of telescopes or a lot of spacecraft in general today would have a field of view of only maybe a couple degrees, and that's like a typical telescope. This mission detected about 2/3 of the total 4,200 confirmed exoplanets. And this mission mainly ended in 2013 because of some technical issues and the fact that it couldn't precisely point anymore because of a couple things that happened. But then after it sort of got stuck in one position, there was a second campaign called K2, and that eventually ended in 2018. But the sort of second iteration of this, called the Transiting Exoplanet Survey Satellite, or TESS, this mission objective is exactly the same as the Kepler Space Telescope, but it covers an area 400 times larger than that covered by Kepler. There's already about 2,000 candidates. It was just launched a couple of years ago, and its payload, instead of having one telescope, it has 4 telescopes, and each of these telescopes has a 16 megapixel CCD array. And on top of that, its field of view is insane. Each telescope has a 24 by 24 degree field of view, and combined, all 4 cover 5% of the night sky, to put in perspective. So these are kind of the main 2 missions that are actually doing the most of the confirmations. I think some confirmations and a lot of the help is done from ground, but this is where a majority of them are confirmed. So now on to my research that I conducted with a small team a few years back at the university I went to, Cal Poly. So the goal was to learn how to image stars that were thought to have exoplanets around them and add to an existing database of exoplanet transits. There's a small observatory dome on campus, and that's the telescope we used for this project, pictured here. It was a Meade 12-inch telescope. And a 12-inch telescope, even though it's like fairly large for just a hobbyist setup, it's really like fairly small to a lot of space telescopes and a lot of the larger observatories in the world. So it's it was pretty cool to me that we could observe these really dim stars with exoplanets around them with just kind of a normal off-the-shelf telescope. We used a monochrome CCD camera. I went over this a bit last week, but having a monochrome camera versus a color camera is really important when taking astronomy data, because a color camera has something called a Bayer filter, and that Bayer filter is actually going to knock down the light and the amount of data that you're actually collecting. But you can always put filters and color correct for any images that you'd like to take with a monochrome camera. And it was mounted on a fork style mount. That name just comes from how it kind of looks like a fork, and it allows complete slewing across the sky. This telescope was also precision pointed, so I think it could point down to about 1 arc minute, which is about a degree in the sky. All right, so now I kind of want to go through all the steps that we would go through for one night of trying to find exoplanets and how we did this. I know this is a bit text heavy, but I'm going to try to make it as clear as possible. Kind of divided it up into these steps. The first thing that we would do to figure out, where are we going to look in the sky? How the heck are we going to know that we're looking at an exoplanet? We would check transit predictions, just like weather predictions, every single day of the summer. We constantly used this database called the Exoplanet Transit Database, or the ETD, and this was our savior. It just listed all the predicted transits for a specific date, how long the transit would be, between what hours, and then as well we would check weather. But even if it was clear, we also had to make sure humidity was at a good level, because we had to be at a certain level of humidity to open the telescope and for it to be safe for the optics. So assuming we had a good exoplanet prediction, or a good transit prediction, then we would go through the steps of setting up the telescope and setting up for a night of data collection. The first couple hours when I first got to the telescope every night was not just going straight to imaging, it was taking calibration frames. These are extremely important for obtaining good data later on and being able to process your data to get the maximum out of your image as possible. So there are two calibration types of frames that we would take, and these are pretty standard in the astronomy data collection world. The first was called a bias frame. This is actually a 0-second exposure, which seems counterintuitive, but this was just to remove inherent sensor or detector noise. So what you see to the right is just an image of a 0-second exposure. So it has nothing to do with the optics or the lens or the telescope. It's just electrons feeding on to the computer, and that's what you get. So you want to make sure those are subtracted out of your final science images so that your images look a lot less noisy and clearer. So we'd usually take 10 to 20 of these, average them together, create what was called a master bias frame, and subtract that out of every single science image later on. The other type of calibration image was a flat field frame, and this removed optical imperfections due to the lens or the telescope. As you can see, instead of it looking grainy, it kind of looks like it's trying to focus light, because now you have a lens, so it's focusing all the light a little bit onto the sensor. It doesn't have to be focused, but you want to just aim for a flat gradient part of the sky. It can be cloudy, it cannot be cloudy, but this will just, or when you combine all your flat fields together and this time you divide them out of the science images, that will help correct for any lens imperfections. So after we take our calibration images, we are ready to point our telescope so that we have maximum precision pointing as possible. Sometimes the telescope can just get a few arc seconds or arc minutes off every night, so it's really important to freshly point your telescope every night. We would usually just slew to a bright star, something that we could see with our eyes and something that looked a lot brighter in the screen than the rest of them. And we would put crosshairs on the screen and just align the center. And in the software that we were using, we could mark the center for the rest of the night, and it would calibrate to that center and be precision pointed for the rest of the night. And the last step we would do before looking for exoplanets is focusing. The focus could actually be different every night because of slight changes in atmospheric effects day to day. So just the fact that we have an atmosphere means that we need to, that our focus can change and the prime focus can be different every night. So how we would do this process is slew to a star, take an image, increase the focus a little bit, take an image, increase the focus a little bit, and do that back and forth. And once we had about 5 or 7 images of that star, we could plot the sizes of those stars and see which one was the smallest. And the smallest one meant that it was focused the best on it. So after this, we can actually go image the host star that we believe that there is a transit occurring. We can't actually see it with our eyes. The image to the right is a pretty typical image, and as you can see from that, you'd have no idea ever which one would have an exoplanet transiting across it. Although for every night, if we had a specific star, we would have to look up a star chart, and when we slew to the star by inputting its right ascension and declination coordinates, which are commonly used to find different objects in the sky, we would slew to the star and then bring up our star chart and just match them like a puzzle. And we would sit there and look at the telescope screen and be like, are we actually looking in the star field that we're supposed to? And if the star chart matched the telescope live screen, then we were pretty confident that we were getting the data that we were supposed to. And some transits last an hour, and some transits can last 5 or 6 hours. So depending on what transit we were looking at and the different predictions on the database that we checked earlier, we would continuously take images, as many as we could, for the duration of the transit to have as much data as possible. And sometimes these exposure times were a few seconds each if it was a brighter star, or sometimes the exposure times would be 300 seconds, 400 seconds if the star was really dim, and we needed to increase the exposure time. So the end result was hundreds of images that look exactly like that one on the right. I think that was one of our old, from one of our old data sets. But I have no idea how which star actually was the one that we were observing that night, but I'll show some data in a bit. So after we have these hundreds of images, what do we do with them? The goal is to perform photometry on each image, which is extracting the apparent magnitude of the host star for every single image. So this can be done manually or automatically, depending on the software you're using. We use something called PyRAF and IRAF to extract relative brightness of each star. And I'd have to go in and highlight the star on every single image and have the software try to extract the relative brightness of each from each of the images, which definitely would take a lot longer than the actual observation portion. And just a refresher on absolute magnitude and the scale that we're looking at. To the bottom right, that's an apparent magnitude scale. And so for reference, the bright stars that we see kind of near city lights are from magnitude 1 to 5-ish, and the naked eye limit is around 7. Again, the higher the number, the dimmer the object is, which is also counterintuitive. But a lot of these stars that we were looking at, I think, ended up being around magnitude 12, 13, 14. So we can't see these stars with our eyes, but the telescope could definitely pick them up. So once we have the extracted brightnesses of all these images, we plot the magnitudes versus time, and then hopefully you have yourself an exoplanet. So this is an example of the data that we got. I think this is the one good plot we got from that research project. Even though we observed several predicted exoplanet transits that summer, we were observing every single night, sometimes a bit of an off focus or too short of a transit, or a dimmer object compared to a brighter object can make the data inconclusive. If there's no distinct dip or lowering of magnitude in your final plot, it's really hard to say anything. And you just wait for the next transit of that planet. Sometimes they happen once a week, once a month, just all depends on the object that you're looking at. So we were just super stoked to see this change in brightness. So this is a transit of planet HD 189733 on July 21st, 2016. And the timescale for data like this and a lot of astronomy data is usually in Julian dates. So that Julian date 2457590 represents July 21st, 2016. And this is just a continuous number, I think, since like 4000 BC. So you can write down a number and it will represent one point in time all the way since 4000 BC, which is pretty cool. And it just makes it easy for astronomers to sort out data over long periods of time. And those fractions from 0.67 to 0.85 are, I think, just fractions of that day. So this transit's probably over a couple hours. And every single data point represents one image. And then on the left, you see the relative magnitude. That's not absolute because magnitude 3 would be really, really bright. This is just the change in magnitude over time. But you can see a dip, and that was really exciting for us. So what did we do with this data, and what is the next step? Back to the exoplanet transit database that I was talking about before, we got to upload that plot to this database and added to the many other astronomy contributors around the world for this specific planet. So that's a plot on the left of every single person who has, or every single data set that's been uploaded for that specific planet that I showed on the last slide. I think it's a plot of time on the x-axis versus the transit time, or the amount of time that people observed it. And the larger dots represent really solid data, and the smaller dots are a little bit more inconclusive. But on the right, you can just see a screen capture of that website. Highly recommend going to it. It's really fun looking around at all the data that people have uploaded around the world. And that site is a huge resource for helping to confirm more exoplanets and add to the 4,200 confirmed exoplanets. So yeah, I think that's it for my portion of the talk. And now I'll hand it back over.
Okay, perfect. Thank you, Ellen. Can you stop the screen sharing?
Yeah.
Okay, good. So we are gonna have some live questions that we have received. We are going to, I'll tell some of them to you and you can answer them, okay? So this question is from Charu Agrawal. Is it said that the exoplanets are made of diamond and graphite?
Diamond and graphite. That'd be cool if we knew that. Unfortunately, we can't know to that detail of exactly what these planets are composed of. A lot of the common parameters that you'll expect are mass, volume, its orbital period, how long it takes to orbit its star, the distance from the star to the planet. Sometimes from imaging spectroscopy, we can get data on composition of the atmosphere, but we can only really make guesses.
Okay, so we cannot really tell what the material that this planet has exactly. It could also be, do you think these exoplanets might also be gaseous planets?
Definitely some of them. I don't think I might be wrong, but I don't think there's a difference in, for instance, these 4,200 confirmed. It's probably an even mix of rocky versus gas-like planets. I think they would still both have the same effect when transiting the star. So really hard to say, but the distance from and the mass from planet to star gives us a lot of good information, and we can guess based on how our solar system is made up.
Yeah, okay. So the next question is from Arushi Katre. It's a bit long question, so it's going to take me some time to read it all and then you can answer. Okay, so she's asking, transit method of detecting an exoplanet and gravitational microlensing are two methods which rely on the light coming from the planet's primary star, and it may take millions of years for light coming from the star to reach us. So is it possible to develop a better way for hunting exoplanets which do not rely on light coming from the source star?
That's a really good question. A method that doesn't rely on the light coming from it. I don't think that I've come across a method yet, because that's a really good point. Everything you're seeing, because it's so far away, is going to technically come from, a certain amount of years back, and it's not exactly what's presently happening. But I'd also say that's true for just a lot of the observations that we make in general, a lot of what we know about our universe. But the transit method really makes up, I think, 80-90% of all the exoplanets that we've confirmed. And then the radial velocity method also relies on imaging spectroscopy, which is just the light that's coming from it as it's moving. So I hope one day, it's definitely something to keep in mind.
That's one point that the scientists could work upon to bring out new methods, right? So that's one working area. Okay.
Project.
So Malhar Date is asking, according to the Doppler effect, we will see the Andromeda galaxy and the Virgo cluster more bluish in the future, right? Then should we see the center of galaxy more bluish after a million years?
That's an interesting point. I hadn't really thought, because I think, if I'm not wrong, the Andromeda galaxy is coming closer to the Milky Way galaxy.
Yeah.
And is coming towards us, then it would be blue shifted. So I don't know how that translates into what we see visibly. What we see with our eyes might be different than its spectral lines that we're getting.
Yeah.
But I actually don't know if it's blue shifting. Does it actually look a little bit more blue to us, or is it just in the spectral data? So that's something I have to do more research on. I'm not sure.
I think, in my opinion at least, I believe that we will see very tiny difference if we are observing the center of the galaxy. Like, we won't really see that much of blue shift, because blue shift appears only when something is going further away from us, right? No. Sorry, what am I saying? Can you explain blue shift and red shift just like in a few sentences?
Yeah, let me make sure I have the blue and red
Yeah, I know.
not screwed up. Um, yeah, so when a star, okay, when so these small movements we can tell by taking spectroscopy data, which sort of gives us a light spectrum of what is coming out of that light source. And you're going to see more blue lines and blue shift in the spectral data if something's moving closer to us.
Closer to us,
And if
yeah.
it's moving farther away, or just relatively, the Earth is here and the object is slightly going this direction, it's going to redshift and show more red lines. So just seeing the difference in these spectral lines from image to image shows that it's moving around and that it might be orbiting.
Yeah, so according to as we think about the center of the galaxy, if it would be blue shifting, I don't think it's an observational data that we will notice very strongly. I'm not
Right.
sure though, but I think that we will observe it more about the galaxies which are, I mean, away from us. I think we'll notice about them more. Okay,
Mm-hmm.
yeah. So the next question, we have Sharina Fernandez asking, is there any chances of life on exoplanets? So like Earth-like planets.
There definitely totally is. I think no one has really ruled it out, but we've also found, no evidence of it. And because we can barely tell the composition of a planet, it's really going to be a challenge and very far in the future when that's actually confirmed or not. But as far as sort of the amount of planets that this is possible, for perspective of about 4,200 of the confirmed exoplanets, and this might be a little bit out of date, but probably about 20 to 50 of them are in the conservative habitable zone. And this conservative habitable zone says like these planets are definitely within the range of distance in respect to its host star where it could hold water and therefore maybe have life. Then there's another longer list of just optimistic habitable zone planets, which is okay, it's sort of near this habitable zone range, but not really. So it's a small percentage, but there's definitely a list of planets. And you can find those lists online that are, the planets that are in the habitable zone and what their masses and orbital periods are.
Yeah, so I think there are these three main parameters which you need to think about when you're thinking about life on the planets outside of our solar system or any planet. The first one is, of course, as you mentioned, the distance of the host planet from the host star. So on this distance, the temperature of the planet is depending upon. So this temperature should be suitable. And since we have only Earth to compare, we need to know that the planet is going around its parent star in about 1 year, so in 365 days, because that's what tells you that it might be in the habitable zone. So first is this distance, second is temperature, and third is if it has water. But then again, as we are talking about water, there might be some extremophiles which might not need water and might sustain on some different
Right.
gases and something like that. So I think the real question here is, does there exist, do aliens exist who are intellectual, or is there life in space? Because when we are talking about just the life in space, I think it has larger probability than the intellectual life existing in space, right?
Right. Yeah. I
Okay.
guess we'll never do that, but fun to think about.
Yeah, right. Okay, so moving on. Again, Malhar Date is asking, what about resolving power of the telescope in that of as Hubble as much has much larger resolving power. So what's the difference?
Difference in resolving power of like these telescopes versus Hubble,
Yeah,
maybe?
I think that's what he means. Yeah.
So I don't have the exact spec in my mind, although I would imagine Hubble, I think Hubble's field of view is probably smaller, although it has spent a lot more time covering the sky. So I think it really looks farther into space, probably has a larger sensor, but maybe has a more narrow field of view, and is looking just really deeply into the sky and taking a survey. Whereas these telescopes, I think the payloads are not as large, but the fields of view are very large, to be able to try to find planets. Yeah, but I'm not exactly sure on resolving power. That's just my guess. The differences.
Yeah, I think it also makes different that Hubble is kind of in the space, so the atmospheric disturbance is not there. So that's why it can capture better data. Also, since we are on the topic of Hubble, I'd like to take the opportunity to tell you guys that we have a free course on Hubble Space Telescope on our website on astronera.org. So you can go there and check it out. Anyway, moving ahead, we have question from Blesson Biju. She has three questions. She or he, I'm sorry, has two questions. Why is direct detection of exoplanets difficult, and what method has found the most exoplanets?
Why is detection of them so difficult? Kind of twofold. Not all stars have planets around them, so the stars that we see at night, only a fraction of them might have planets around them, or we just haven't stared at them long enough. And the other part is that a lot of stars that we are looking at are just so dim that you need to take, or you need, a certain type of telescope or certain size to be continuously looking at it. It's also, I think, the amount of time taken to actually confirm something. You might get a data set like the one that I got, and clearly there's really good evidence that it's there, but that doesn't mean it's confirmed. Either a combination of methods or, seeing a transit maybe tens of times might finally confirm it. I'm not exactly sure what the confirmation process is, but I know that it has to be pretty sure before it actually goes into a database. And those are mostly using the space telescopes. So it'd be hard for me to get evidence that, like, hey, this might be a planet, we should confirm this.
Okay, got it. So Pragun is asking, so does this graph of apparent magnitude versus time show the magnitude of a single astronomical body over time? And is it using this graph that you conclude whether the body is an exoplanet or not?
So, or I guess exoplanets, in relation to this apparent magnitude scale, the actual exoplanet itself is probably a lot dimmer. What we're observing to be able to confirm the planet or not is its host star. So imagine, I guess, a really dim star, really far away. All that, or even just getting the light from that, is going to block out any light coming from the exoplanet by tens of times of magnitudes to our perspective. And that's why we can't directly look at these exoplanets. We have to look at the stars and make guesses about, how the star and planet are interacting together to be able to confirm these. But the magnitudes of the stars really can be all over the place. I know there's a couple bright stars that we can see with our naked eyes that do have exoplanets around them. And then there are stars that are up to magnitude 20 or 30 that we've been able to detect with large telescopes that also have exoplanets around them.
Okay. So this question by Ishan. How do you calculate the mass of the exoplanet?
Calculating the mass. I don't know the exact process, and I've never done it myself. but the relative size of it and the relative change in brightness from just imaging the star and then watching it transit in front of it, and also knowing the star's mass can, I think, help deduce it. That would be my guess for how it's done.
Okay. Kunal is asking, where can we learn more about the data analysis and coding process you showed in the presentation?
That is a good question, because the specific method that I use to do photometry is a very broadly known process, and you'll find that all over. Although the specific IRAF and PyRAF software that I used, I'm not sure how much information is out there. I learned from a couple people around me because it was a very specific process. Although I will look into that and make sure to mention it next week, because I think it'd be cool to have resources for how to, do that specific extraction method.
Yes, sure. I'm sure that everyone's gonna have more questions, and we are running out of time now, so we will definitely cover them on our social medias. Ellen will answer them, or we can also cover them in our next session, as she just mentioned for this particular question. So thank you so much, Ellen, for joining us today. And next week on 14th of August in the same time at 7:30 p.m., we are gonna go imaging the black holes, which is really interesting. So hope you guys will join us then. And that is it for our today's Astro Stream. Stay tuned for next week's session and go on astronera.org for more about astronomy. You can find lots of e-learning courses there. We have recently released course about how to photograph Milky Way, which you can find. So enjoy learning astronomy while you're quarantining. So see you guys. Bye-bye.
Thank you. Bye.